Okay, let's talk more about the network covalent atomic solids. There aren't a lot of elements that do this, but carbon is one of them and is probably the most interesting. So elemental carbon exists in several different forms. You can have graphite and diamond. Those are the two we're most familiar with. We call those different forms of the same element allotropes. I have no idea why, but there it is, allotropes. It's a new word. So graphite. Graphite is the substance in your pencil. Some students think it's lead because it's a lead pencil, right? Yeah, the Romans used lead in their pencils, and they used lead in a lot of things, and they had lead poisoning and went insane and destroyed their own empire, right? There is no lead in your pencil. Let's just get that off the table. It's graphite. It's carbon. Okay? In graphite, the carbons are covalently bonded to each other, but that occurs in these flat sheets of interconnected hexagonal rings. So you can see here that the carbon atoms are bonded to each other in these hexagonal rings, but it's a flat two-dimensional sheet. And then there's another one and another one. And what holds those sheets together is just dispersion forces. They hold together because it's a big area, but it's only dispersion forces. And that's what makes graphite slippery. That's why when you rub your pencil across the paper, some of it stays behind and leaves writing, right? It's also useful as a lubricant. You can use graphite as a lubricant. Like in a door lock or, squeaky something. You can actually even use your pencil lead to put a little graphite on there and ease the squeak because it's slippery. Graphite's a good electrical conductor because in these hexagonal sheets, we have extended pi bonding networks. So that goes back to our bonding theories, where we learned that we can have delocalized bonds. And so in these delocalized pi bonds, we can have electron movement. So carbon conducts electricity. So that's graphite. Graphite has a density of 2.2 grams per cubic centimeter. You don't need to memorize that. But if you take graphite and you put it under extremely high pressure, you can force the carbon atoms to rearrange and get closer together. And that's how diamonds are formed. Graphite, under extreme pressure, rearranges the carbon atoms to form diamond. A diamond has a density of 3.5 grams per cubic centimeter. So can you make diamonds out of graphite? Yes, you can. Is it economically feasible to do so? Maybe. Usually you get more money out of it if you find them laying around or you dig down in the ground. So the natural diamonds have formed deep under the surface of the ground. You can synthesize them. You need pressures of like 50,000 atmospheres at temperatures of 1,600 degrees. So this isn't something you're going to be able to do at home. In the diamond now, we have the carbon atoms covalently bonded in 3 dimensions instead of 2 dimensions. So each carbon atom, let's look at one of these in the middle, like this one. This carbon atom is covalently bonded to 4 other carbon atoms. And we've learned before that carbon likes to form 4 bonds. So this is going to have a tetrahedral arrangement of those bonds, and we're going to get tetrahedral holes in there. The structure is similar to the zinc blende unit cell, except we just have carbon atoms. We don't have 2 different ions. Diamonds have high melting points, 3,800 degrees. So like if your house burns down, may be hard to find, but if you had a diamond ring in there, the diamond would be just fine. It would come through a house fire, no problem. Diamonds conduct heat very well, which make them useful for abrasives and cutting tools. So if you're trying to grind something smooth or you're trying to cut through something, You want something that's going to be able to withstand the heat generated by all the friction in that. Diamonds can do that because they don't melt, and they can conduct the heat away to other things. So there are other less commonly known forms of carbon. One was discovered back in the 1980s, and they discovered this by aiming a powerful laser at a carbon surface. And you might think, well, why would you do that? Just to see what happens, pretty much. It's kind of one of those Friday night experiments. So they discovered a new form, and they call it Buckminster Fullerene. So Buckminster Fullerene occurs as a soccer ball-shaped cluster of 60 carbon atoms. So 60 carbon atoms, and it's a big open sphere, and each of these rings is a hexagon. So it kind of looks like a soccer ball. In general, we call them fullerenes or buckyballs, and they can range from 36 to more than 100 carbon atoms. Any questions? Yeah.
The picture there, it looks like the carbons only have 3 bonds. Is that just the way the picture looks, or do they actually?
They do only have 3 bonds. That's a good observation. So here, each carbon is only bonded to 3 other atoms, and then there's got to be some delocalized pi bonding going around. Yeah. Like in the graphite, there were only 3 bonds as well. Good observation. We've also synthesized long carbon structures called nanotubes. So these are sheets of interconnected C6 carbon rings that form cylinders. So it's a lot like chicken wire. It looks like chicken wire, doesn't it? With the little hexagons. And so if you imagine chicken wire rolling around and making a tube, you can form a single-walled nanotube. It's called a nanotube because it's really, really small. So you can have a single-walled nanotube. You can also have multi-walled nanotubes where you've got a bunch of nanotubes nested inside of each other. Nanotubes are really strong, 100 times stronger than steel and 1/16 as dense. So here you've got something much stronger than steel and much lighter weight than steel. So you can imagine that that's going to be useful. Nanotubes are useful for lightweight applications requiring strength. So golf clubs. You know, you look at these golf clubs at the store, and oh, this has a graphite golf club. Well, yeah, it's carbon-based. Is it the same as the graphite in your pencil? That wouldn't work. No, it's carbon nanotubes, carbon fibers. A bicycle with a graphite frame, it's nanotubes. You can also make wires out of these because they conduct electricity. You can bundle nanotubes together and form really, really tiny wires. You can also form nano ribbons. So this is just like a long sheet of this C6 rings. It's called graphene. And so here's another illustration of a large graphene sheet. And these graphene sheets, that's what we talked about on the first slide of this chapter, about them discovering this material that was transparent, impermeable to all substances, and only 1 atom thick. That's the graphene. Another important group of network covalent atomic solids are silicates. Silicates are extended arrays of silicon and oxygen. And this is the most common by far network covalent solid. It makes up about 90% of the Earth's crust. So most of the Earth's surface has silicates in it. So you think about going to the beach, and what's at the beach? Sand, right? That's kind of what makes a beach. There's a bunch of sand near water, right? Do you know there's a beach in Reedley? there actually is, Reedley Beach. It's on the river, but it is a beach. There's a lot of sand there when the water's down. People go there and swim in the summer, and they die too, but yeah, it's an awesome place. So sand, these are used, silicates are used in ceramics, cement, and glass. So what we call silica has a formula of SiO2. So there are 2 oxygens for every silicon. And so if we look at this, we see we've got these tetrahedrons where there's a silicon in the middle, and it's covalently bonded to 4 oxygens. But this oxygen is bonded to another silicon. So it's not SiO4 because these oxygens are shared with other silicons as well. So the overall ratio is 1 to 2, 1 silicon and 2 oxygens. And of course, these can arrange in different ways. Quartz is just one form of silica.